So in this example problem, we're going to calculate the burst speed for a rotating disk. But so in the problem we're given, we're saying that we have a flat disk that has an outer diameter of 0.5 meters. All right, it has an inner diameter of 0.1 meters, and it has the disk has a thickness of 0.075 meters. Okay. Then we said that that this disk is shrunk onto a steel shaft. There's a shaft going through it, and that shaft has an approximate diameter of 0.1 meters. Okay, both of these are made of steel, and they have the following material properties. All right, so we're going to then we want to determine the following things. The first thing we want to determine is if this assembly is going to be run at 6900 RPM, what is the required interference, or delta, that we need to solve for the problem. The second part of the problem asks us for what is the maximum stress when the shaft and the disc are not rotating. So if omega is equal to 0, what is our maximum radial and what is our maximum tangential stresses? When omega is equal to 6900 RPM, we're also asked to find what is sigma r and sigma theta. Okay. And then what is the maximum allowable speed at which the shrink fit will loosen? And then the final part is what is the allowable safe speed for the disk, the burst speed of the disk alone, if the maximum tangential stress in the disk is going to be equal to 50 megapascals. All right. So we're just going to break this problem down into each of the parts and solve each one by one. Okay. So the first part, or part A, we're going to solve for delta. All right, and we want to find out what is delta at 6900 RPM. So we can say that delta is going to be equal to the change in the radius of the disk minus the change in radius of the shaft. Okay, so we know that the change in radius of the disk is going to be equal to the radius of the disk divided by the Young's modulus of the disk times sigma theta minus the Poisson's ratio times sigma r. Right, at the inner radius. Right, this is where we're interested at. Right, so we know due to the boundary conditions that sigma r is going to be equal to 0 at this point. So we only have to really care about sigma theta. All right, so sigma theta. All right, so if you plug in for sigma theta, which is equation 30 in the packet, what we end up getting for our change in UR of our disk is going to be equal to 0.0026 times rho omega squared divided by E. Okay, so all right, then we can then do the same thing. All right, and we can do the same thing for the shaft. So you can say for the shaft, if we solve the same equation, all right, what we'd end up getting is we get 2.1875 times 10 to the minus fifth omega rho omega squared divided by E. Okay, so if we plug in our value for rho, our value for E, and our value for omega, all right, and we solve all of these, and we plug in the value of U of R for our disk and for our shaft into our equation for delta, we end up getting our equation for delta is going to be equal to 5.25 times 10 to the minus fifth meters. Okay, so So that's our interference of our between our two disks. All right. For part B, it asks us to find what is the maximum stress when the system is not rotating. Okay. So what we can say here is that our interference pressure is going to be, which is equal. We can use equation 26 to find our interference pressure. All right. And if we plug in all the values that we have, what we end up getting for our interference pressure is we get 100.8 megapascals. Okay. For part C, all right, it asks us, all right, all right, I guess so. Sorry, one last thing. So to find sigma r and sigma theta, in this case, we just need to plug in our values of use equations 12 and equation 13 to solve for sigma r and sigma theta due to our pressure. All right. So in part C, it asks us to find what would be the stress when the disk is rotating at 6900 RPM. So at 6900 RPM, we need to calculate what is our value of we need to find out what is we have our rotational pressure. So I guess at 6900 RPM, we would need to find our we need to find sigma r due to our rotation. We would need to find sigma theta due to our rotation, and then we can find our total sigma r and our total sigma theta by adding the values of sigma r omega plus sigma r due to the interference pressure. And then we can do the same thing for our tangential stress. We just add the stress due to rotation plus the stress due to the interference pressure. All right. And then the last thing, the part D asks us at what speed will the interference fail? So if we find, so what we can do here is we can have, we can say that delta, our interference, is going to be equal to UR of our disk minus UR of our shaft. Okay, so if we plug in our original delta that we solved for part A, so we said plug in delta when delta is equal to the delta that we solved for part A, which was equal to 5.25 times 10 to the minus fifth meters. All right, and we can then solve for U of R disk and U of R shaft. So these are both UR disk and UR shaft are equal to sigma R, or functions of sigma R, total sigma R and sigma theta total. All right, for both the shaft and the disk. So if you plug in those values, we can then solve for everything in terms of omega. All right. So all of these will all have omega squared terms in them. So we can then solve for omega. All right. And if we solve for omega, we should then be able to we can then solve for the omega that would correlate with or correspond with the displacement delta at 5.25 times 10 to the minus fifth. And then the last part of the problem, part E, asks us to solve for the burst speed at sigma theta max. So we want to find the speed at which the maximum stress would be equal to omega. So remember, for a component, all right, for a stress element, that for you will have our tangential stress and we will have our radial stresses. All right, for a thick-walled cylinder, these are our principal stresses. Okay, so we want to know when our sigma max is equal to 50 megapascals. So either sigma r or sigma theta is equal to 50 megapascals. Um, um, that's when the the disk will burst. So what we can do here is we can say that sigma, our maximum allowable stress, is going to be equal to 50 megapascals. All right, which is going to be equal to rho omega squared divided by 4 times 3 plus v times our inner radius squared minus 1 plus v times um, our um, inner radius squared. All right, this equation is because r was equal to our inner radius. All right, so that's where our maximum stress is going to occur. And so if we solve for omega, this will be your burst speed. All right. Okay. So the last part of this, I guess, or the one comment I would like to make about this last part is that we didn't consider the interference pressure in this case because we're asked to just determine the burst speed of the disk alone. So we were assuming that this disk was spinning on its own without the shaft inside in order to calculate this burst speed. Okay, so so the only stresses we know that sigma theta max is going to give us their highest stress. It's going to be higher than our radial stress at any point. So that's why we selected sigma theta. And then we know that the sigma theta's maximum value will always occur at the inner radius.